Okay, if there is BPR, your temperature distribution diagram would still be, of course, following the same principle where there is no BPR. But this time, the way you determine the summation of BPR will be BPR1 plus BPR2 plus BPR3 and so on and so forth. This depends on the number of effects that you have. So what I have written here is a general formula in determining the summation of BPR. Why there's a need for you to initially determine the summation of BPR for your multiple effect evaporation system? It's important because you need to determine this time what we call as the delta T effective, or the effective delta T. The effective delta T will not anymore only be this time dependent on the difference of the steam temperature and the temperature of, let's say, the last effect, but you need to subtract also from this one the summation of the BPR. The summation of the BPR that you have here. So you are to determine the boiling point rise depending on the saturation temperature of each of your effects, saturation temperature of each of your effect, and the solid content of each of the effects. If you recall, we determined the BPR from the Durin's chart. Okay? We get the BPR from the During's chart. The During's chart gives us the boiling point of the solution. So you can get the BPR by subtracting from the boiling point of the solution the boiling point at saturation of that same solution, should it had been that its solid content is negligible, or shall we say it is dilute. So you need the two information, the solid content and the saturation temperature of a particular effect. That way you can determine this BPR of each of your effects, and that you already know how to get it. You get it using the Ring's chart. You need two information. Again, you need the X of that effect, or the XL1 or the XL2 or the XL3 of each of your effects if you have a triple effect evaporation system, together with the saturation temperature of each of your effects. That's what you need. That way you can get the boiling point of your solution, subtract it from the subtract the saturation temperature from that, so that you will have the BPR of your each effect. You have to take the summation of those, and that would be your summation of BPR. Your original summation of delta T now will be summation of delta T effective, because you will now subtract the summation of BPR from the original formula, which is temperature of the steam minus temperature of the last effect, whatever is your last effect. This is how you're going to determine the summation of delta T. So all your formulas now, this time, when you determine the delta T, for example, delta T1, will now be summation of delta T. I will place here effective. Same formula. You have 1 over U1 over 1 over U1 plus 1 over U2 plus, depending on the number of effects that you have in your multiple effect evaporation. So the only thing that changed here is this formula, because you already subtracted the BPR. And the formula for determining the delta T1, the delta T2, and the delta T3 will still be in principle similar in form also to no BPR, but we just changed this one. Instead of summation of delta T, it's now delta T effective. Now, what about the temperature distribution diagram for such a particular scenario wherein you have a BPR? This is what it's going to look like. I will just construct here for a double effect evaporation system. That way, it will not be taking much time. So I will divide. Okay, I will still have temperature of the steam here. And this is the temperature of the last effect. Let's say T2. Okay, your T2 would have been, So based on our procedure in multiple effect evaporation system, I'll place here another broken line. Okay. Uh, this is your saturation temperature 2. You get it from the operating pressure of the last effect, let's say in this case, the second effect, from the steam table. So you will have your T saturation. You have here your T of the steam. So I'll just copy it here. For example, that's T of the steam. What you will have here in this temperature here, you will have the BPR1. Your second effect would have boiled at this saturation temperature. But since there is already BPR, it's going to elevate. It's going to increase the boiling point to this value. So from this particular illustration now, the true boiling point of effect number 2 will be TS2 plus BPR2. Sorry, BPR2. This should be BPR2. Why did I write BPR1? So your saturation temperature for second effect plus the BPR2 you determined will give you the boiling point of the second effect. This is now the elevated boiling point of the second effect. What do you have from this distance to this distance? This will be your summation of delta T2. Now, after delta T2, supposed to be, this will be your saturation temperature 1, right? No BPR. But since your boiling point has elevated, so you will have a corresponding BPR1 for the first effect. Then the temperature here will be your BP1. And that would be your saturation temperature supposed to be for effect number 1 plus the elevation, the boiling point elevation 1. Then this would be your delta T1. Now, how do you check whether you're doing the right thing or more or less what you're doing is within allowable range of values? You have to add all of this. This plus the BPR2 is this. This BP2 plus delta T2 will be this. This will plus BPR1 will be BP1. BP1 plus delta T1 will be your temperature of the steam. They will all add up just like what we did in the normal scenario wherein we don't have BPR. They should all add up and reach the temperature of the steam. That is in the case of multiple effect evaporation. Now, what's the difference then in the manner in which we do material balance, or shall I say specifically energy balance for each of your effects? When you do material balance for each of your effects class, you are not going to use the saturation temperature, this one and this, in determining the enthalpy of the solution, but rather you're going to use this. You're going to use now the BP1 and the BP2 in determining the enthalpy of your solution for effects 1 and 2 respectively, not the TS1 and the TS2, because this time you have already the BPR. Now, in some cases, actually in majority of cases that I have solved already, let's say whether it's double effect or triple effect evaporation, uh, there is a formula that the problem already specifies. Even the problem specifies the formula in determining BPRs for each of the effect. What I mean by this is you will fully understand if you will read the sample problem of John Couplis on a particular problem wherein there's no need for you to go to During's chart to find the BPR1, BPR2, BPR3. The problem itself gives you a formula based on the solid content of your solution so that you can determine already the BPR in such a way that you won't have to go to the During's chart using your saturation temperature and solid content to get this. This time, you only need the solid content and you are already able to find the BPR for each of your effects. When you have done that, then you compute for this one, and then once you have this, compute for the summation of delta t's and construct again this diagram. Anyway, you know how this is done. All you have to do is add up, just like there's no BPR in the case of our double effect evaporation sample problem. Add up. So saturation temperature plus BPR, boiling point temperature. Delta T2, that would be TS1. Plus BPR, that would be BP1. Delta T1, that should give you the steam temperature. If there should be a deviation, allowable deviation here in the steam temperature, that would only be at most 1 or in decimals. If it goes beyond 1, probably there's something wrong with the values or the formula that you are using. The rest class of the procedure in multiple effect evaporation is the same. It's all the same. And you can, probably some of you have already read it in Jean Couples. It's still the same. The only thing that changed is this manner of determining the boiling point of your solutions, because you're not anymore using the saturation temperatures in determining your enthalpy for the solution, and even the enthalpy of your vapor, because this time it will have already the superheat, and you will need the BPRs for that. And you need the BP of the solution instead of the saturation temperature. Okay, so before I go to crystallization, I place already in Canvas your things to work out. So I place it there already. You need to work it out. Anyway, it's still 1 week after that you're going to have the submissions of those. The other one is to be submitted on the last day of the midterm exam. Okay, do you have any question here before I go to crystallization? The formula, this formula, this is the same formula you find in John Couples. Actually, he did not place this one, but it was discussed there that you are to subtract the summation of the BPRs from your original summation of delta T. Excuse me. No question here? Okay, excuse me, class. I'll just drink water. So if there's no more question, I'll stop sharing in this part. Then I'll go to crystallization. I'll stop sharing here first.